Hello everyone, welcome to this session of class 9 mathematics, and I'm your Anu again. This class, it's a continuation of the last class, that is we saw problems. We started with exercise 5.1 in the chapter Introduction to Euclid's Geometry, isn't it? So this is a continuation of exercise 5.1 problems, and today it is the third problem. So let us start. Consider two postulates given below. That is, given any two distinct points A and B, there exists a third point C which is in between A and B. Okay, so understand clearly, given two distinct points A and B, they are distinct points, and there exists a third point C. There is another point C which is in between A and B. Okay, there exist at least 3 points that are not on the same line. So there exist at least 3 points which are not on the same line. So which are not on the same line in the sense they are non-collinear. They are not collinear, they are non-collinear points. Now to the question, do these postulates contain any undefined terms? So we have seen in Euclid's postulates and theorems that there are some undefined terms. As we saw it in the last class, we saw a plane is not well defined, a point which is which is which is dimensionless, which has no part, isn't it? And the lines, they need to be defined properly. So likewise, are there any undefined terms here in the given statements, and are these postulates consistent? Do they follow Euclid's postulates? Explain. So first we need to spot out the terms which are undefined in the given postulates. See, given any two distinct points A and B, there exists a third point C which is in between A and B. So it is not very clear for us whether A, B, the distinct points A, B, there is a line in between A and B, a line formed with A and B, and if C exists on the line segment AB, isn't it? So we can also draw it in this way. Distinct points A, B, C. There are 2 points A and B, and if C is in between here, between A and B, it can also be a curve like this. It can also be a circle where A and B are points and C lies in between A and B. It can anyway be be like this. So they have not specified whether it is a line which joins A and B. They have just said there are two distinct points A and B, and there is a third point C which is in between A and B. So it is not defined. It is not clear for us whether A and B, there is a line segment between A and B, that is which joins A and B, if there is a line, or if C exists in the line formed by A and B, formed within A and B. So that is not clear, so that is undefined. Next is, there exist at least 3 points that are not on the same line. So they have said there are 3 points which are not on the same line. The next thing which has to be defined or which is not defined here is about the plane. So here in even the first part, the points A, B and C are not specified as to whether they lie on the same plane or in the different plane. So we can't assume. So it is not very clear, or it is not very defined, clearly defined whether they all lie on the same plane or not. So the second part too has the same problem. We don't know whether the 3 points lie on the same plane or on the different plane. So these things are not defined properly. So do these postulates contain any undefined terms that we saw just now? Are these postulates consistent? Yes, they can be consistent. Now they are inconsistent because we don't know very clearly as to whether A, B are endpoints of a line segment and C lies on the line. It is not very clear for us, but it can be consistent under 2 conditions. That is, when C lies on the line, C lies on the line which has points A and B. If it is like this, it is consistent. The postulate is consistent because we are clear that C lies in between A and B. And if it is not on A and B too, see, if it is somewhere else, it is not on A and B, if it is outside, if it is in the exterior region to AB, then too we are very clear that C doesn't lie on A and B, lie on AB, the line segment AB, and it lies outside AB. So in these two cases the postulates are consistent, but here we have some terms which are undefined, so it is not consistent. And do they follow Euclid's postulates? No, actually Euclid's, it doesn't follow Euclid's postulates, because Euclid's postulates, yes, deals with intersecting lines, parallel lines, and then about circles with radii, isn't it, and parallel lines too. So these the postulates given here, or the statement given here, is according to the axioms, the length axioms and the line segment axioms. Okay, so that is about the first question. Now that is the third question in the exercise 5.1. Now let us go to the fourth question. If a point C lies between 2 points AB. Now let us draw this so that you will have a clear idea. Fourth question. If a point C lies between 2 points, see, now it is very clear for you. There is a line segment AB as its endpoints, and C lies between them. Between them you have the point C, such that AC is equal to BC. AC is equal to BC. It is clearly given. So C is the midpoint, isn't it? Because AC is equal to BC. The lengths are equal. The lengths of the two parts AC and BC are equal. Therefore C is in between. That is midpoint. Now you need to prove that AC is equal to half of AB. So now how do we do that? So we are very clear from the figure that C lies in between A and B, and AC is equal to BC. So we know AC is equal to half of AB. But how do we prove that? According to Euclid's axioms, we need to follow the Euclid's axioms, and we need to prove AC is equal to half of AB. So now how do we do that? Now take the given statement. So given is AC is equal to BC. Okay. So we have equated AC is equal to BC. They are equal to, they are one and the same. Now what do we do is, we add AC to both sides. So adding AC to LHS and RHS, AC plus BC. Why do we add AC? Because AC plus BC gives us AB. We need to get AB here. So AC plus BC. What is AC plus BC? It is nothing but AB and 2 times AC. Nothing but 2 times AC is equal to AB. Naturally that is also true, isn't it? So AC to AC is equal to AB. Now what is this statement to do with Euclid's axiom? Let's see. See, AC plus AC is equal to AC plus BC. We have written here. We have added an AC extra to this equation. See, the equation states AC is equal to BC, isn't it? So according to Euclid's axiom, what does he say? When equals are added to equals, see, AC and AC are added to equals, then the wholes are equal. So the statement follows Euclid's axiom. When equals are added to equals, AC, BC equal, isn't it? So when equals, that is AC, is added to the equals, then the whole that is the addition, the sum, are equal. Okay, so that is 2AC is equal to AB. Okay, so that is how we get AC is equal to AB, which means AC is equal to half of AB. We take 2 to that side, it gives you AC is equal to half of AB. So we have AC is equal to half of AB, thus proved. Do you understand? So it follows the Euclid's axiom. If equals are added to equals, then the wholes are equal. Okay. Now we'll move on to the next one, the fifth question. The fifth question extends, the fourth question extended. So we have in fourth question, in the given fourth question, point C is called the midpoint of AB. We know that point C, isn't it? Because it is in between, and AC is equal to BC, therefore C is the midpoint. Prove that every line segment has one and only midpoint. So if there is a midpoint for the line, can there be any other midpoint in that line other than the midpoint? If it is possible or not possible, let us see. Okay, so let me draw a line AB. Let me take C here to be the midpoint, or let me take Q and P and Q to be two midpoints. Now let us assume, okay, so this we will prove that the line segment, every line segment has one and only midpoint by the method of contradiction, because first we take that there are two midpoints in a line segment. We'll see how we prove that there is only one and only midpoint for the line segment. So by method of contradiction, we start proving AB is a line segment, and let there be two midpoints P and Q. Okay, if P, let us take first P to be the midpoint. If P is the midpoint, then what do we have? We have AP is equal to PB, isn't it? This is one condition. When P is the midpoint, we have AP is equal to PB, like previous one. When Q is the midpoint, we have AQ is equal to QB, isn't it? So when P is the midpoint, we have AP is equal to PB. When Q is the midpoint, we have AQ is equal to QB. Now what happens is, I add AP on both sides. That is, AP plus AP is equal to AP plus PB. Okay, do you understand? See, AP plus AP is equal to AP plus PB. This follows the Euclid axiom. Which one? We did previously. Now the fourth sum we did, that is when equals are added to equals, the wholes are equal. So according to the axiom, AP plus AP is equal to AP plus PB. Now 2AP is equal to, what is AP plus PB? That is AB coincides with the line segment AB. AP plus PB coincides with the line segment AB, so it is nothing but AB. Now let this be 1, equation 1. Okay, now let us consider Q to be the midpoint of AB. Now we have AQ is equal to QB. Here I add AQ on both sides. That is, AQ plus AQ is equal to AQ plus QB. Okay, now forget about this P. You just see Q, AQ is equal to QB. We add AQ on both sides. So we get AQ plus AQ is 2AQ, and AQ plus QB is nothing but AB. So let this be the second equation. Do you understand? So this also the same Euclid axiom. When equals are added to equals, the wholes are equal. So what happens is, you just observe the equation 1 and equation 2. Compare equation 1 and equation 2. We have the RHS same. See, AB. It is same, isn't it? So what we write is 2AP is equal to 2AQ, which implies AP is equal to AQ. Do you understand? AP is equal to, so AP is equal to AQ, which means P and Q are one and the same. P and Q are one and the same, because AP is equal to AQ. AP is nothing but AQ, isn't it? We can replace P by Q or Q by P. So we get P is equal to Q, isn't it? So P and Q are one and the same. But P and Q are one and the same. We have got the result P and Q one and the same. But this contradicts our assumption in the beginning that P and Q are different midpoints. So our assumption is wrong. So what we have is P and Q are one and the same. So there can be only one midpoint, one and only midpoint in the line segment. Do you understand? So P and Q are one and the same. There are no two different midpoints. There cannot be two different midpoints in a line segment. So that is what the statement proves. Now, how do we get? Actually, this is according to the Euclid axiom. This step, according to the Euclid's axiom, I said when equals are added to equals, the wholes are equal. I said. Now, how do we get 2AP is equal to AB? From this, 2AP is equal to 2AQ, because see, equals, when the equals are when the equals are equal to the same thing, then they are equal to one another. When things are equal to the same thing, when things are equal to same thing, see, 2AP is equal to AB, 2AQ is equal to AB. So when things are equal to the same thing, then the things are equal to one another. that is 2AP is equal to AB, 2AQ is equal to AB. They are equal to the same thing, AB. Therefore, 2AP is equal to 2AQ. So that is according to the axiom. When things are equal to the same thing, then they are equal to one another. 2AP is equal to 2AQ. When doubles, things are equal to their doubles, then they are equal to one another. So that is 2AP is equal to 2AQ is nothing but AP is equal to AQ. So according to the axiom. So we have 3 axioms followed in this statement problem. So AP is equal to AQ. From this we conclude there is one and only midpoint for a line segment. There cannot be more than one midpoint for a line segment. Isn't it? Hope you understood this. Now let's see the last problem for this class. In figure, if AC is equal to BD, then prove that AB is equal to CD. So I have drawn the figure here. Let me draw it more clearly. See, you have A, B, C and D. So what they have given in the figure, if AC is equal to BD, when AC is equal to BD, this is given. Okay. So what we need to prove, AB is equal to CD. So we need to prove AB is equal to CD. Okay, so this is the sum for you. So we need to prove AB is equal to CD. So now how do we proceed? See, AC is equal to BD is given. Now let us take AC. What is AC here according to the diagram? According to the figure, what is AC? AB plus BC, isn't it? AB plus BC. Okay. Now what is BD? BD is equal to BC plus CD. Do you understand? So what is AC? AB plus BC. And what is BD? We have BC plus CD, isn't it? Now what we do is AC is equal to AB plus BC and BD is equal to BC plus CD. So in both the equations we have BC here. See, BC is common to both the equations, isn't it? So what I do is I subtract BC from both the equations. Okay. So AC minus BC. So I subtract BC on both sides for the first equation. AC minus BC is equal to, when BC gets subtracted you have AB, just the AB. Okay. AC. Then from BD I subtract BC. What do I get? Just the CD. Okay. AC minus BC is equal to AB and BD minus BC is equal to CD. Okay. So, what is this actually? AC minus BC is equal to AB and BD minus BC is equal to CD. This is according to a particular axiom. That is, when equals are subtracted, by equals, then they are equal to one another. Remainder is equal to one another. So that is what we have done here. AC minus BC is equal to AB plus BC minus BC. BC gets cancelled. So we have just AB, and BD minus BC, BC plus CD minus BC. BC gets cancelled. We have just CD. So this is according to the axiom. When equals are subtracted by equals, then the remainders are equal. So this is according to the axiom. Now we have AC minus BC is equal to AB and BD minus BC is equal to CD. So now what is the next step actually? The next step is, see here AC and BD. What is given? AC is equal to BD, isn't it? So AC is equal to BD. Therefore, what we do? We conclude AB is equal to CD. How it is? See, AC is equal to BD, isn't it? So AC minus BC, this BD can also be replaced by AC minus BC. So this part becomes, LHS becomes equal in both the equations. So we get AB is equal to CD. Do you understand? So things which are equal to the things which are equal to the equals are equal to one another, since both LHS of both the equations are equal, because it is given AC is equal to BD, we have AC BD here. Okay, so these two equations, the LHS of these two equations become equal. So things which are equal to equals are equal to one another. So AB is equal to CD. So that is how we prove AB is equal to CD. AB is equal to CD. Do you understand? Sorry, AB is equal to, given that AC is equal to BD, we have AB is equal to CD. Do you understand this? So this follows, this statement has one of the axiom, like when equals are subtracted by equals, then the remainders are also equal. That is how we get the two equations. And when equals are equated, things are equated term, and things are equal to equals, then they are equal to one another. Here the things are AB and CD, and the equals are AC minus BC and BD minus AC. BD minus BC, because AC and BD are equal, it is given. So things which are equal to the equals are equal to one another. So AB is equal to CD. So that is the conclusion. Okay, so you just need some time to, take some time to remember all the axioms. In this chapter you have Euclid's axioms. Axioms are separate and postulates are separate. Axioms do not need any proof, isn't it? They are statements, they are universal truths actually. They don't need any proof. We don't need to prove them. They are just statements, and postulates and theorems need some proof. And we have also seen that before. So you just take time to remember all the axioms and postulates and recall them whenever you do sums like this. You need to justify your steps whenever you do, because this this chapter is very important for you, because it carries some 25 to 30 marks in your for your whole exam, in all the chapters together. So please concentrate on this chapter and do by heart all the axioms and postulates as far as possible. Okay, so with this we end this class. We have still some more problems in this exercise, and we have still another exercise 2 with 2 or 3 problems. We'll see you to the next class. Until then, it's bye from Anu. Thank you.